Welcome back to Orlando Math Learning Academy. So as far as we learn all the basic function and its graph, in this lecture we will learn that all those functions can be modified in terms of position and characteristic. However, the shape is still the same. We can the concept of the modification, we call it a transformation. It means that we can move a function up or down relatively to the original function, or we can stretch or compress a function to get a new function, or we can move to the left or move to the right to get a new function. Okay, so let's put the topic today: transformation. Okay, so let's take a look at the first type of transformation. We call that vertical shifting. Vertical shift. Okay, and the function we want to shift is the absolute function, y equal to fx equal to absolute of x. We want to shift this function up or down at with a certain unit. Okay, and the graph of this function it can be obtained by using the table. So let's set up the table, and we want to compare the table of the original function, which is this function, to the one we will be shifted. Okay, x fx. Okay, if x equal to -3, fx equal to 3, -2 equal to 2. If x equal to -1, we have fx equal to 1 because we take absolute value of all negative. If x equals 0, we have fx equals 0, 1, 1, 2, 2, 3, and 3. And from this table, we can obtain the graph. You can obtain the graph. Okay, so x equal 1, this is 1, 2, 1 is 1, 1 here and 1 here, we have 1, 0 here, 2, 2, we have 2, and 3, 3, we have 3. So we have the graph look like this. Okay, so we already learned how to graph this in a previous lecture. Okay. Now I want to shift this graph up or down with at a certain unit. For example, I want to shift this function, this graph 5 unit up, okay, or 3 unit down, for example. Okay. If I want to shift 5 unit up, then the new function or 3 or 2 unit up, then the new function become this. 0, 0 become here, 1, 1 become here, this point here become here, and so on. So we have the shape like this. Okay, so you see that the shape is still the same. However, the characteristic and the position is changed. Okay, so the vertex right now is not at the origin anymore, but it's at the point 0, 2. So what we did is we add 2 units to the y component of each point, right? So 0 here, because instead of we keep the x component, so we add 2 unit to the y coordinate, so this one become 2, this one become 3. Let's say instead of 1 1 we have 1 3, because 1 2 3 here, 2 here, 1 here, and instead of having 2 2 we have 2 5, so 2 here, 1 1 2 3 4, 2 forms, sorry, 1 1 2 3 4. Okay, or we do the same where we shift 1 unit down. We keep the x component and we subtract the y component by a certain value. For example, subtracted by 1, it means that we move down 1. Okay. So for vertical shift of the graph, what we have to do in general is we add the y component at the we add a y component of each point of the graph to a constant c, right? Okay. So given y equal fx, for the vertical shift, we do is the new function we have is y equal to fx plus c, and then this is moving up c unit, or we have y equal to fx minus c, moving down c unit. Okay. Example. We have fx equal to x squared and fx equal to x squared plus 6. So the function, the graph of this function can be obtained by moving 6 unit up, from moving this function, moving the graph of this function 6 unit up. Okay, so you can graph the function fx equal to x squared and then move up 6 unit relatively. Okay, hold on, let me close this a little bit here. It keep popping up. Just I don't know why. I think I just go ahead and close this. I'm sorry. Disconnect here. So we will have okay, let's grab the function. I just want to scale it. Okay, so the function of fx equal to x squared is something like this. Okay, and we move up this function 6 unit. So move up this function 6 units. So for example, from here to here is 6. Okay. So next, let's investigate the horizontal shifting. Okay. So similar to vertical shift, instead of moving up or moving down, we will have the original function move to the right or move to the left. Okay. Okay, let's do this function. Y equal to fx equal to x to the 3rd power. Okay, and set up the table for this function. We have this x, fx here. We have -2, -1, give you 1, 0, give you 0, 1, give you 1, 2, give you 8. Okay. and the function will be like this. Okay. So for the horizontal shifting, we want to keep the y component of each point, and we modify the x component. So instead of having -1, we will have a new value. Instead of 0, we have a new value. 1 and 2, we have a different new value. We can add or subtract the x component of each point to a constant. Okay. So for example, I want to move to the right. I subtract the x component by another constant. I want to move to the right. For example, I want to move to the right 2 units. So I subtract the x components by 2. So instead of have -1 and 2, we have -3, 1. We have -3, 1. We have -2, 0. We have 1 minus 2 is -1, 1. We have 0, 0, 8, for example, right? Okay. So we would have something like this if we want to move to the right. Okay. And if we want to move to the left, we want to add the x component to this constant, to a certain number. For example, we want to move to left, we add by 2. It means that we add instead of 8, instead of 2, 8, we have 4, 8. Okay. Let me see. Shift it to the right. Right. Or instead of having 1, 1, we want to move to the left. We have negative, for example, -1, -1, 1, for example, because we subtract it, right? Okay. Okay. So in general, we have this. We have y equal to fx minus c. I see. Then we have moving to the right. If we have y fx plus c, then we have the original function move to the left. Okay. Okay, let me see. I don't know if we can use this for example. I may have to make up something else. So this is original function. This one is the original function. Okay, so we want to move to the right, right? If we want to move to the right, it means that we 0, 0. Yeah, we add. Okay. Oh, I think I said something not true. I think I said something wrong. I had a mistake, I believe so. We want to change. Let me see. X. We want to keep all the y. Yeah, we want to keep all the y component, and we change the x component. Yeah, so for example over here we want to move the right to the right 2 unit. So this is, instead of that 0 3, we have 3 0. So over here 3 0. Okay, so instead of having 1 1, we have 4 1. Okay, we have 4 1. Okay, so what I say is right. Okay, this is one okay. Example. Y equal to x minus 12. I want to graph this. So in order to graph this one, I grab the basic function. I want to get the basic function look like this, and because you see that the x component is subtracted by 12 unit, it means that we move to the right 12 unit, and with the shape is still the same. So move 12 unit from here to here, so it's 12 unit, so the shape will be like that. Okay. It's original function. Okay. Okay, so for the transformation, we also can flip the original function about the x-axis or the y-axis, not just by shifting up or down or left or right. We can do the reflection. Okay, number 3. Reflection. So if I have the function like this, this is a square root function. So I can make it reflected about the x-axis. So the new one will be like this. Okay, the new one will be like that. Let me use the red color. So you see that the shape is the same, but the position is different. So that what did I do? What did I do to the function? Basically, instead of having square root of x, I apply the negative sign to the radical of the function. Okay, so the new function we have instead of having a square root of x, we have square root of negative square root of x. So I apply this negative side to the whole function. By doing that, the whole function will be reflected about the x-axis. Okay. Okay. Or I can make it reflected about the y-axis. I may have something like this. Okay. So what did I do? I just applied the negative side to the radicand of the radical. Okay. So the new function is like that. It becomes square root of negative of x. Okay. This is I apply to the whole new apply the negative side to the whole thing. Okay. Okay. So if given a function f(x), y equal to f(x), okay, and if I apply the negative side to to the argument of the function. Okay, then we have it reflecting about the y-axis. If I apply negative sign to the whole function, then we have reflecting about the x-axis. Okay. 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 Next. So the new function can be obtained by stretching or compressing the original function. Okay, stretching and compressing okay. So for example, if I have a function like this, a square and a quadratic, basic quadratic function, y equal to x squared, the new function by stretching vertically could be like this, or compressing vertically, like become like this. Okay. So what do I do? In order to obtain this one, the new function must be in the form y equal to ax squared, with a is less than 1. A is between 0 and 1. Okay. A between 0 and 1. And in order to obtain this function, the new function must be in the form y equal to ax squared, but a is greater than 1. For example, y equal to 3x. Okay, and this one, for example, y equal to 1/2 the x. Okay, so basically what I did, oh, let me see, I think, no, this was greater than 1, I'm sorry, a greater than 1, and in between 0 and 1. Okay, so for this function, for the stretching vertically vertical function right here, what we do is we just keep the x component. However, the y component will be a factor of the x component. Will be stretched by the factor of an a value right here. So for example, over here we have the 1 1, right? If we had a function y equal to 3x squared, so it'll become 1 3. So we keep the x component, but the y component is stretched by the factor of 3. Okay. Example. Y equal to 1/2 absolute of x. Okay, so the absolute of x have in this form, and because it's 1/2, so between, you see the a component, the coefficient, the leading coefficient, between 0 and 1, so it become like this. We keep the x component, and the y component is decreasing by the factor of 1/2. So instead of 1 1, we have 1.5. That's why it become wider. The shape of the new graph become wider. Okay. Okay, let's go through some practicing problem. The one that has the one that is more complicated than the example I gave to you. Okay. Practicing. I want to graph the function f(x) equal to -3 x plus 5 square plus 3. Manually. I want to graph this manually. Okay, so first of all, what we have to do is we have to find the original function first. So by looking at that, I see the original function is the quadratic function, because as I have the power of 2 over here. Okay, right here. So I want to graph the original function first. Okay, the original function will be like this. Okay. Okay. Then I apply 3 unit up, right? Because remember f(x) plus c. I have f(x) here, and I add the original function is x squared, and I add the original function to a constant c, meanwhile we moving up 3 unit. So I move up 3 unit. So the new one become this. Okay. Then I move to the right 5 unit. Okay, because this is in the form f of x plus c. Okay, f of x plus c. Okay, is in the form. So I move to the right 5 unit. 1 2 3 1 2 3 4 5. So they become this. Okay, because 1 2 3 4 5. Move into the right 5 unit. Then I'll make it reflected about the x axis, because it's in the form f negative fx, right? It's negative fx, negative of the original function. So I make it reflected over the x-axis. So become what? This is 3 units, so it'll be 3 units down here, right? 1 2 3. So it become like that. Okay. Then afterward, I need to have it stretch vertically by the factor of 3, because it's in the form a of fx, with a is greater than 1. Okay. So by the factor of 3, so the new function will become something like this. Okay. So what we're doing is just sketching the graph. Okay, we don't really graph it. So let me put the function so that you know this is y equal to x squared, and this is y equal to x squared plus 3. This is y equal to x plus 5 squared plus 3, and the blue one here is y equal to negative x plus 5 squared plus 3, and finally we have y equal to negative x plus 5 squared 3 plus 3. Okay. So it's not that hard. You see that we can obtain a new function based on the original function by transformation. Okay. So after we learn transformation of the function, we learn another property of the nonlinear function. We call that average rate of change. You already heard that terminology in the previous video lecture video, and in the past lecture video, average rate of change is basically the slope of the linear function, right? But for the nonlinear function, the average rate of change is basically the slope of the line that connecting 2 points on the curves. Okay, and that line we call it the secant line. Okay, so let me see, 1 2 3 4 5. I need to check the number here, so I don't know what number we are. So last time we do number 4 and this is 5, so this one must be 6. Average rate of change. Okay. Okay. So if I have the graph of a nonlinear function, something like this. This is nonlinear function, and on this curve I pick 2 points. Okay, and I connect these 2 points to create a line, and we call this line is a secant line. So the average rate of change in the nonlinear function is basically the slope of the secant line that connecting 2 points on the curve. Okay, and the formula for the average rate of change is also m equal to delta y over delta x equal to f of x2 minus f of x1 over x2 minus x1, with x1 x2 is the components of the point. I name it point A here and point B here, with component x1 fx1 and b is x2 fx2. So you see that it's not much different from the slope of the linear function, right? Not much different. We in the linear function we have m equal to y2 minus y1 is over x2 minus x1. So basically fx2 is the y component, fx2 is y2. Okay, so just instead of but for the this average rate of change of the secant line, it's just the line that connects 2 points on the curve. Okay, so that's the only the different things. Okay. Next, 7. Difference of quotient. Difference of quotient. Okay. So in part 6 over here, we had a formula for average rate of change of the secant line. In part 7, the different quotient actually is a general form of is a general formula for the average rate of change. Okay, and this formula is applied to the interval. It's applied to the interval on the x-axis. Okay. Okay. For example, okay, if I have the graph like this, okay. And at the point here and the point here, the point here I have component is x, and the point here I have component is x plus h. Okay, because I add x to I move the x to the position x plus h, so the distance from x to x plus h is h. Okay. So the average rate of change of the function of this function here between x and x plus h, we call that difference of quotient, because it's the average rate of change, so we can apply this formula also. So it become m equal f of x plus h minus fx over x plus h minus x. So the difference of quotient become fx plus h minus fx over h. Okay. And these 2 points here, let me connect these 2 points. This formula is also represent the slope of the secant line here. Let's do the example. I hate it every time I need to fix the screen. Oh, okay. I want to calculate the difference of quotient of function fx equal to x 2x minus 5. And the formula for difference of quotient is what? Fx plus h minus fx over h, right? So we need to calculate f of x plus h first. F of x plus h, it means that I replace the x with x plus h, so become 2x plus h minus 5 minus fx. Fx is the whole function here, but when I subtract the difference, I have to open parentheses, so I distribute it. And I simplified it, so I have 2h over h, then I have 2. So it means that the difference of quotient for this function over here we have is 2. Okay. So when you replace the x with x plus h here, it is kind of the same as we evaluate the function at certain point. Remember when we evaluate function, for example, we evaluate function of fx equal xy at 3, we replace x with 3, so become 9, right? So this is the same over here, but instead of the constant value, we have a variable x plus x, and fx is the whole thing, 2x minus 5 already, so we don't really replace or anything. We just bring the whole function 2x minus 5 to the formula here. Okay, let's do one more example. Let's pick one of the example, one of the problem in the practice section. Okay. I want to do number 70 on page 256. Number 70 on page 256. It wants us to find the average rate of change. Okay. Find the average rate of change of the function fx equal negative 3x squared minus 4x from the point from negative 6 to negative 2. Okay. Okay, so I will let you think about this problem for a few seconds, for a few minutes, then I'll come back to help you with that. All right. Okay, so how you do this? Because we want to find the average rate of change, so we have to use the slope of the secant line, right, at 2 points. Okay, at 2 points. Okay. Okay. So the slope of secant line, what we have? The slope of the secant line is the formula is m equal to f of x2 minus f of x1 over x2 minus x1, right? So they give you x2 and x1 already, because it is said here from negative 6 to negative 2. That is the x component of 2 points. Okay, so we need to find the y component. That's what we need to. Well, that's what we need to find. It means that we have to find f of negative 6. Okay, I replace here. So it give you what we have. What we have give you this is the 36. 36 times 3 is let me see. Oop. 36 times 3 is negative 108, and this is 24 plus 24 equal negative 84. Okay, and f of negative 2 is negative 3, negative 2 squared, negative 4, negative 2 give you negative 12. Plus 8 is negative 4, right? So I have f of x2 and f of x1 already, because x2 and x1 is right here. Then I have the average rate of change equal to negative 4 minus 84 over x2. This is x2, negative 2 minus negative 6. So this is negative 4 plus 84 over negative 2 plus 6. So 80 over 4, 20. So the average rate of change, or the slope of the secant line between 2 points here is 20, equal 20. Right. Let me see, I can pick another problem to do. Let's do one of the problem with transformation. Okay, let's just do the problem let's do something really hard here. How about we do number 40, page 252. Okay, and we want to sketch the function 1/2 cube root of x plus 3 plus 4. Okay, so we do this. Every time I need to fix the screen here. Okay, so by looking at it, I see that the leading coefficient is a half. It's a cube root function. This is we add 3 units to the argument, okay, and we add 4 units to the whole function. Okay, if we add 4 units to the whole function, it will mean that we move up 4 units, right? Okay, but first of all, the first step what we have to do is we need to recognize the original function. The original function in this case is a cube root of x. Okay, and because it's cube root of x, so the graph will be something like this. All right. So this is cube root of x, and we want to move up 4 units. Okay, we want to move up 4 units, so it becomes like this. Because I add 4 to the whole function. Then I want to move to the left 3 units because I add 3 to the argument. I add 3 to the argument, it means that I move to the left 3 units. So I move to the left 1 unit, 2 unit, 3 units, so the origin become here. So the new function will be something like this. Okay, so this is cube root of x plus 3 plus 4. Then I want to stretch by 1/2, by the factor of 1/2, because I want to stretch, so it's kind of elongated along the y component. So the new function will be, try to use a different form. Let me see, I have a different color. Okay. So the new function will be like this. Oh, I don't have another color. I have red, blue. Okay, I have this. So something like that. Okay. Because I stretch it vertically by the factor I have, so the elongate is elongate about along the y axis. Okay, so the new y axis is right over here. The new y axis is here. After we shift it to the left 3 units, this is the new y axis, so we want to sketch it so it's elongate along the new y axis right here. Okay. So I mean, for transformation, when we sketch the graph using transformation, it's not really hard. Okay, but when it depends on how the question want you to do. If they want you, if it wants you to sketch the graph by transformation, then that's all you have to do. But if we want you to really graph it, okay, then you have to consider the accuracy of each one. Okay, for example, if they really want you to graph this function, you have to put consideration, you have to put the coordinate of each one of the graph into consideration over here. So the one of the point of the graph of cube root of x is 1 1, right? 1 1. Another point is 20 0 0, of course 0 0. Another point will be 27 and 3. So 27 is a really long one, 3 here. So 3 here. So this is 27 here. Okay. Then for every time you shift up, down, left, right, or you sketch it, or you shred it, or you compress it, you have to put the coordinate of each point into consideration. It means that the y, sometimes the y component will be shred by a factor of half, Okay. In this case, the y component will be, instead of having 1 1, and instead of having 3, let me see, as this point here we move it 3 units, so the coordinate of the point here is 1 2 3. So instead of having the 2 1 2 3 1 2 3 4 5 2 5, so we will have 2 and hold on, oh, this is compression. I'm sorry, this is compression, so it cannot be this. I'm sorry, it must be like something like this. I'm sorry, no, not this one. Okay, so instead of having 2 5, we will have 2 and 2 2.5. So the new function like this. I'm sorry. Okay, not this. Okay, so you must be very careful, because each point will be the coordinate of each point will be changed. So you need to put that into consideration when you really graphing the function, the new function. Sketching is easy. Okay, so I think that's all for the lecture today. So I'm afraid I will be off the lecture for about more than a month, because I'm coming back to Asia, but I will be back on the June 17 to start section 3.3, which is a piecewise function. That concept is very easy too. So yes, so if you have any question, you just need to put your comments under the YouTube video. And if you want me to go through some certain problem, you just put a comment under the YouTube video also, then I may answer your question on YouTube. Okay, but from now on until June 17, I will be off the YouTube to do my own business in Asia. Okay, so hopefully I'll see you soon. Okay, all right, so that's all for today. Then I'll see you in more than a month.